So before I forget, concerning next week, so I propose that we meet on Wednesday. Is this at 1? Yep. Okay. All right. So okay, so this will be. So today I start with the last chapter, chapter 7. Where hopefully we'll see the end of the proof. So again, I start with recalling what we are, where we are. So we so in the previous chapter we constructed essentially a morphism of T spectra. So and this is on smooth varieties from the T spectrum representing the Ram cohomology to something which looks like as follow. And so the main piece is this Z check. Fine print. So and so let me also recall a little bit how this Z check looks like. So this Z check is a T spectrum. On some big site over some diagram, which is so this is a T spectrum on regularly stratified schemes over some double star scheme, which is or diagram of schemes indexed by this category that we have seen many times. And so on level in level M, it's given as the Godman complex associated to some flaggy pre-sheaf, which is like this. Okay, and now I describe this here, which is somehow the main object in defining the spectrum. So Z is it's a flaggy pre-sheaf, and so it takes a 4-tuple. Like this. So this is I alpha is an object in this indexing category. X double star will be a P double star scheme or P I alpha double or P double star I alpha scheme, and this is a flag in X11. So to this thing, Z is given as follows. So it's a homotopy colimit, which is indexed by some category which is denoted by A, and it's associated to X double star and the flag. And it's given it's a homotopic limit of the following complexes: R gamma. So it's the Ram cohomology over U. I think it's probably U0. So yeah, U is a stratified scheme, and this is the open thing. So and then of some module with integrable connection of logarithmic type, M, and then tensored with higher, so direct image, derived direct image of 1. Okay. Right. And now, I can also now maybe tell more about this. So remember that this A x star of t. So this is the category of squares of the following shape: m plus x11 and u. So this is just so this is data which is associated to this 4 tuple, and then we complete some of this diagram, make it commutative. These are usually denoted by px. This is qx. I think this is su. This is ru. And so so mu is essentially the non-derived direct image along this map of some module here, which I think is denoted by n, and it's of logarithmic type. And this is the derived. So then some of the other part is given by the derived direct image along this map of the unit. All right. So this is what we have, and so the goal of this chapter. So the goal of this chapter is somehow starting from this. So we want to construct a map or morphism of spectra from the homotopy limit of the Čech complex associated to omega to this truncation of omega. And this is somehow the main objective of this course. Okay, so this is what I want to explain in this chapter. Okay, so before really starting, I want to make some small modifications, essentially without really proving anything about this about the right-hand side here. So so that there is first fact, which is it's a theorem which I will not prove, which says the following: the natural map from T tensor M G lower star of sorry, C to G lower star is an A1 star HHH local equivalence. And here, so A1 star, this is the following diagram. So spec K, A1. Okay, so this is, of course, there are different choices of intervals on star-star schemes, but the one which is somehow relevant is this one here. So I will not prove this. It's not very hard, but it will take us some time, and so since I want to finish, I will assume this. And so this somehow this tells us that we may so as a consequence we may replace the spectrum Z here by the infinite suspension spectrum on Z hat 0. Okay, this is how this is used. Okay. Sorry? Yeah, but yeah, anyway, this is not very difficult really. I think it's. I mean, this guy is not. I mean, Z hat is not so far from being a suspension spectrum, in fact, because I mean, essentially it's a suspension spectrum if you think in terms of flaggy presheaf. So this is just passing from flaggy presheaf to just sheaf somehow. It's. I mean, I agree. It's an important point, but yeah, I decided not to prove this. Okay, so this is one simplification. There is another, actually more serious one, which I will also somehow assume or. So maybe let me write this. So, so thanks to this theorem, I somehow as a corollary. So just like this, we may replace this spectrum by essentially the infinite suspension. So there is, as I said, there's a more serious thing which I will do, which is really not. I mean, yeah. So see, a more serious assumption. What do I say? Simplifying simply. Assumption is the following. So is that I will somehow so I do as if there is no lambda infinity, let's see, on the right hand side. So it's not anymore on the blackboard. So remember, so we had a map going from omega to something where we have to somehow to stabilize. So this is stabilization of spectrum. And it's really crucial to stabilize the spectrum. Otherwise, there is no such map. I will. But somehow this really causes a lot of trouble later in the argument, and so I decided somehow to do as if there is no such operation. So I just somehow describe what happened if we don't have this. So the reason why I do this is because I think that the main so the main ideas will be already apparent without having to deal with this, yeah, it's again it's a choice of things that I will not describe. Okay, so I hope it's fine. I mean, I might somehow later at some point say where the trouble is and how to deal with it. Okay, but it's really, I mean, it's really how to say, it's a bit cheating in some sense. So, oh, this is really yeah, it's an essential difficulty that one has to solve here. Okay, so okay, so as I said, from now on, I will do as if we have a map from omega to so I introduce this notation. I'll denote by P star. This is the composition of these operations. So I just give a name to this, and I will assume that there is a map from omega to sigma t infinity sorry, put G. Like this. Okay, and so I start from here and tell you how the argument goes. Okay. All right, so let me start with some preparations. Okay, so I need to introduce some notations. First, let's consider the following category, which is somehow some kind of a triple integral. So I think if I want to write this correctly, this would be probably the integral over this thing here. On flags, and then of A. Okay, so what are the objects here? So the objects here are given by, so objects are 5 tuples. Okay, so this is as before, and this U is in A of X star. Okay, so okay, and so we have two. We have so we have 2 functors that I think we have seen this. I've seen them before, which I denote by make regular singular, where these 2 interrogation marks, they belong to either 1 1 1 0 0 1 0 0. Okay, so should I remind you about this? It's the usual. Should I remind you about this? Huh? We did not define this?
Like we said regular singularity, but defining some very different ways, right?
You mean I did not define these categories?
No, we did define but we didn't say what regular singular means.
Oh, but okay, I mean. But so these were defined, I think, these 2 functors.
There were 2 cases.
Yeah. So yeah, exactly. So we have these things. So and so these are functors from that goes from this category to abelian categories or Tarnakian categories. Okay. So and so we have 2 complexes of presheaves on this category with values in make 0 0. And let me remind. So we have already seen them. So the first one is given by so is this M, which I will not maybe yes, which is of logarithmic type. And the second one is this RS lower star, of which will also mean. We have seen this today, I think. All right, so we have these 2 things. And so I now introduce some notation somehow to somehow a bit more convenient. So we define a pseudo-natural transformation. This epsilon that goes from make 0, 0, two complexes or vector spaces. So this is considered as a constant two functor, and which is given by just given by taking the derived global section of M tensor to something. And so I hope this makes sense. So so this is given by a collection of functors that depends on these 5 tuples. And so if you fix this 5 tuple, then the functor is given by taking global section over U of mu tensor with something. Okay. Right, so with this notation, let me just write it again. So the flaggy presheaf that somehow appeared earlier today now can be written as whole colimit of U of this epsilon applied to R S U lower star. And so we then somehow we can think about this object as obtained by applying this transformation to this thing here, which is also, I mean, this is also a presheaf with values in MIC. Okay, so we have this, and now we consider the following cosimplicial object. So now consider the co-augmented cosimplicial object that I denote by X underline with a dot, which is given as the Church complex of RS lower star. Okay, so this is I mean, this is the same thing as here. Right? So we have this complex of presheaves with values in MIC here, and so this is an algebra, and we associate to it the Church complex. Okay, so this is a co-augmented cosimplicial complex of presheaves on this triple integral with values in MIC 0. Okay, so and this is augmented. So let me tell you how it's augmented. So the x minus 1 is just the unit. Okay, so in degree n, this is just tensor product n plus 1 time of this object. Okay, so Okay, and from this object we now associate also another cosine object, which is x without the underline, and so this will be a co-augmented cosimplicial complex of flaggy precies, and this is it's given as follows. So if you evaluate this on a 4-tuple, then this is so by definition this is the homotopy colimit on this A of the sphincter epsilon applied to the x dot underline of the okay. So of course it's clear that x0, this is just the z that that appeared previously in the theorem. Okay, so we just somehow extended the z to some augmented cosimplicial object. Okay, so it's not really. I mean, it's very close to the Church complex associated to z, but it's not really the same. Okay, it's somehow we do the Church construction, but somehow not on z directly, but rather on somewhere a bit deeper than in the construction. Sorry?
Why here is x0?
Here? So I'm just saying that so this is a cosimplicial object. I'm saying that in degree 0 it coincides with the z.
Okay.
This is the z that appeared before. Okay. So in degree -1 it's it's just colimit of gamma of epsilon of 1.
No, I thought it was that was the equivalent of gamma. Sorry, so this is also augmented.
Yeah. So this is co-augmented cosimplicial complex of Laggy precies.
What is the -1 value?
The augmentation is just is a homotopy colimit of gamma of epsilon of 1. So it's if you want it's the cohomology of u with values in M, in the module M. Okay, so it's easy from the construction that we have the following statement. Let me maybe write it as a theorem. So which follows from the previous theorem that I stated today and the construction. So there exists a morphism of co-augmented cosimplicial T spectra between the thing that we are interested in, the Church on omega, and the following thing. So so we apply. So this is this pi, big pi star to G lower star. Infinite suspension Godman complex of chi dot h. Okay, so so the strategy of the proof is to show that is to compute the homotopy limit the right-hand side. Or at least some significant quotient of this homotopy limit. And in fact, so the goal will be to show somehow. So roughly speaking, we will show that the homotopy limit of the right-hand side coincide with augmentation. So it will be given by pi upper star, g lower star, sigma k infinity, Godman complex of chi minus 1 made fibrant. So we will show that this cosymmetrical object somehow is acyclic, which would give that the homotopy limit is this. And then from here, it's not difficult to conclude. So once we are here, we just we try to have our hand on this object and try to compare it with what you want. So at the end, we will construct really a map quite easily somehow from here to here. Okay, so somehow the main part of the argument is to show that the homotopy limit simplifies and gives us this here. Okay, is this clear? The easy step is to go from here to here. It's relatively easy to go from. I mean, you have this guy. This is rather simple. As I said, this is just. So if I have an underline, this is just 1. Right? So this is just. There's less cohomology, if you want, in here. And this can be analyzed, and one can construct a map quite easily from here to here. Okay, I mean, one construct a map from here to this thing actually, and this is rather obvious. But then somehow the point is to show that this here is -1 connected. So we have such a map here, and then we show that this guy here is -1, so -1 connected. Yeah, so somehow really the main point is to pass from the homotopy limit of this to this. Okay. Okay, so and somehow to compute this homotopy limit, so the idea is to show that. So again, roughly speaking, we will show that this cosymmetrical object, so this cosymmetrical object of pre-sheaf with value in mix 0, 0. Is contractible. It's contractible, but it's not enough to show that it's constructible. One has to do this in some strong sense that I will make clear later. So we need to have this contractibility in a strong sense so that we can pass it through all these functors that appear there. And so we will do this by the one key ingredient is the fact that so this is I mean this is remember this is a Chech on K0. And so the key ingredient is or the key point is that this X0 can be enriched with a mixed hot structure. Okay, so I'll maybe first say a bit more about how you can put this a mixed hot structure on this object. So this is not, I mean, this is not very difficult, but let me go through this. So the idea is as follows. So I mean, basically this guy is given by a direct image functor, and we know that direct images they have mixed Hort structure. So this is basically the idea. So, but I want to do this somehow more precisely. Okay, so okay, so to do this properly, we consider again the two functors that I denote by VMH that exist for 1 1 1 0 0 1 0 0, and which are defined similarly as make regular singular. So, for instance, so these are two functors on this gadget. So VMH 0 0 applied to 5-tuple. What is this? This is simply VMH of U0. And what is VMH? This is the category of ind variations of mixed Hodge structure. So of course here I have chosen an embedding of K in C. Okay, and the same for, let me just do one, for example, 0 1 of the same, saying this is VMH of M0 X 0 1 T. Okay, so we have these things, and so I can somehow repeat the construction. So I define X underline 0 and put a Hodge here. This is by definition just R S lower star of the unit, but now the unit as a Hodge, as a variation of Hodge structure. Okay, so this gives us pre-sheaf on this triple integral with values in VMH 0 0. And I can also do the Church construction on it. So I have the co-augmented version. Yes. And of course, if I have a variation of mixed Hort structure, I can look at the drum component And the DRAM component of this will not be a priori x0, but there will be a map from the DRAM component of this to x0. So let me write this maybe. Okay, so maybe before, just let me also again introduce the version where there is no underline. This is, as you expect, this is given. So this is a homotopic limit over use of so psi is a Hodge of the underlying version. And what is this guy here? This is just the previous epsilon composed with the forgetful functor DRAM. So the f DRAM is the thing that goes from a variation of mixed sort structure to make regular singular, and this is just the DRAM component. Okay, so we have this version of the thing that I was considering previously. Now, here's a fact. There is a natural map or natural morphism of pre-sheaves from the Hodge version, where you forget everything except the DRAM component. That maps to the previous one, but it's not not an isomorphism. Not an isomorphism a priori. I mean, it's not an isomorphism. And but still, it induces a morphism of flaggy presheaves from x dot Hodge to x dot. Of course, simplicial object. Okay, and so now the point is the following. So, lemma. So also, this is not an isomorphism. It's as good as an isomorphism. Namely, if you look at the Godman complex, map induced on Godman complexes, it's in each degree, and this is an HH local equivalence. Okay, so I will not give the proof, but just so what is behind this? So proof. So this boils down to Bailinsson's lemma which says that basically that direct images, that all kind of direct images, they coincide generically. Okay, so I mean, Bayes' lemma would tell you that the naive direct image, which is just the derived one, I mean, the thing that I'm using all the time, this, for instance, this guy here, this is just the right adjoint to S upper star. Generically, it coincides with the right one, which is given by, for example, by the de Rham complex. I mean, there are two kind of direct images. I mean, let's do it. Maybe just let's do the simplest case. So take the spectrum of a function field over some base field k. So here you have you can look at for example, the Tanakian category of let's say, a variation of mixed source structure over k. Okay, this has meaning, and this has enough injectives. So you could compute the X group here, or even X group and enrich in mixed source structure, for example. Okay, but a priori, I mean, it's not clear that that has to do with has anything to do with the direct image. Okay, let's do the simpler case. Let's just work first with this guy. Okay, so here you take a module with integrable connection. You can look at its direct image, which is just a complex of k vector spaces. But this is it's unclear that this has to do with the de Rham cohomology with values in this module. Okay. Right, so there are two things. That is, if I call this P, that is the R P lower star of a module M, and then there is the de Rham cohomology of the module M. Okay, and these two things are a priori different, but in fact, thanks to Bayes', we know that they are the same up to isomorphism. But this is really special to the fact that we are. I mean, if I have enough fine smooth variety, this will not be true in general. Okay, this is because I pass to the generic point. These two things become isomorphic, and there is a similar story for variation of mixed source structure. You can compute direct image in two ways. So they will give you a priori two different two different mixed source structure over the point. And Bayes' tells us that these two things are the same, and moreover, they are compatible with the forgetful functor. Okay. So this is what's behind this, and of course, you imagine that you have to go locally in order to apply this kind of facts. Okay, so somehow, yeah, thanks to this lemma, we can now do as if we have, or we can just replace chi by chi Hodge. So these were somehow the preparations. Now let's pass to this second paragraph, which will be so here I will describe the ingredient that comes from Hodge theory. Okay, so somehow motivated by this discussion here, we now put ourselves in the following general situation. So let C be a small category endowed with a functor alpha from C to smooth varieties. So C, of course, will be this triple integral, and alpha will be just setting this 5 tuple to U. Okay, this is somehow the example I have in mind. So we consider the two functor that I denote by variation of mixed Hodge structure, and now I consider this from C to categories and takes x to be an H of alpha x. Okay, so we assume that we are given. Assume that we have, let's say, DG algebra A. Let's see, just an algebra A in the category of, so in complexes of pre-sheaves on C with values in V and H. Again, the A that I have in mind will be this x0 Hodge. So example. Let's see. C is this A, and A is x Hodge. All right, so and so what we are interested in is, of course, we would like to have, so we are looking for condition that ensure that condition ensuring that the Church complex on A is strongly contractible. Yes, there are two A's, but in this, so in this paragraph there will be one A, except in this example. Okay, so if you forget about this example, there will be one A. In the example, there is an A because it entered in the category C. But okay, so
this example is not small, is it?
Essentially small,
Okay.
which is okay. I mean, small. You mean the category is not small, right?
Yeah, the category is not small.
Yeah, but it's essentially small. So it's up to replacing this by an equivalent category, it will be small.
Okay, so
It's as good as small. So let me first make precise what do I mean by strongly contractible for a consimplicial object. select definition. So let B be an co-augmented co-simplicial object. Let's say just I do it for complexes of presheaves, but it works complex of presheaf on C with values in PMH. And again, so it really makes sense in much bigger generality. So I'll say that. So we say that D is strongly contractible if for every integer there exists another integer n such that the obvious morphism from total plus b smaller than n plus 1, and so n big N plus small n to dot plus smaller than n is 0 in the derived category. So let me tell you maybe what is this. So dot plus b smaller than n. This is the total complex of the following double complex that start in the at the augmentation. So this is in degree -1 up to Pn and then 0 afterward. Okay, this is what I mean by dot plus. Okay, so there are obvious morphism, which is just the one that you see directly, sending identities and then 0 afterward. And we want these to be these morphism to be 0 if you fix n and then for some big n. Is this clear? So this is what I mean by strong contractibility, and this is a condition that somehow behaves well when you apply functors. So if you have a cosimplicial object B and you apply to it some functor, if B dot is strongly contractible, then the image by this functor will be also strongly contractible. Okay? Any reasonable functor that preserves quasi-isomorphism will have this property. Okay, so the idea is to show that this chi or the Church complex on chi or this chi underline Hodge is strongly contractible, and then we can apply to it all these functors that we have and get something which is strongly contractible, and then this can be used to compute the homotopy limit. Okay, so if you have something which is strongly contractible, then the homotopy limit of B is, of course, B minus 1. Okay? And this maybe write it. So why are we interested in this definition is because this condition implies that the homotopy limit of any functor, let's say f applied to B, it will be just B f applied to B minus 1. So now I can state the main result in this paragraph. This is the following theorem. All right, so we assume the following condition. It will be on this algebra A. Okay, so and this category C and so on. So the first condition is the following. So there exists an integer n such that for every object in C, the dimension of alpha x is smaller than n. So the dimension is bounded by n uniformly. Second, we assume that again for every x in C, alpha x is so-called an Artin neighborhood. So I don't know. You know what is an Artin neighborhood? An Artin neighborhood is so it's an affine, it's a smooth affine scheme which has so essentially so it's x has some admits a sequence of maps like this to the base field, where these are relative curves having good compactification. Namely, so they are affine curves, and they have a compactification which has where the divisor is étal over the next one. Okay, this is the notion of Artin neighborhood. Okay, so the third condition is the following. So the end variation of mixed Hodge structure, again for every x, ax, mod out by the unit, so this lives in VMH alpha x. So this end variation has weight larger than 1. Okay, so said differently, the GRU for the weight filtration of AX is 1 Hodge for n equals 0 and 0 for n negative. And of course, it can be anything for n positive. Okay, so these are the conditions, and now the conclusion is the following. So then the co-augmented co-simplicial object Church on A is strongly acyclic. And more precisely, we have the following. We have information about the n that we need. So dot C check less than n plus 2n plus 1 A is 0 in the Rath category. All right. Sorry.
The n.
Yeah, it's the same n.
Is independent of little n.
Exactly. Yeah. In this situation, it's independent of little n. Yes. So I'm going to sketch the proof of this theorem. Okay, so let's maybe say convenient to set B dot to be the stretch of A. Yeah, so let me also draw some notation. So we have O, this is a pre-sheaf on C given by O of X, O of alpha X. Now the alpha X are affine, so this is just the coordinate ring of X. So we have a functor, let's call it denote this by O, that goes from pre-sheaves of C with values in variation of mixed structure to pre-sheaves of modules on C, of O modules. And this is simply just taking, on X, let's say on X, this sends M to, if you want, F the RAM of M, global section. Okay, so we have such a thing. Okay, so I'll split the proof in two parts. So let me. So part one, I will prove the following statement. So here we show. So maybe before saying what I will show, let me also introduce some extra notation. So I will need to consider not only algebraic function, if you want, but also C infinity function. So I'll denote C infinity, the pre-sheaf, again on C. Oh, there are two C now. Okay, so this is a, I don't know, okay, given by C infinity at X. This is the C infinity of alpha X, maybe analytic complexified. Okay, so we have two pre-sheaf of rings on C. That's the O, and then C infinity. Okay. So the part one of the proof is consists in showing the following. So here we show that the cosimplicia, cosimplicial object OB tensored with C infinity is strongly acyclic. And even more, we will see that so the n that appears here is just equal to 1. So in fact, more precisely, O of B smaller than n dot plus plus 1 is 0. So okay, so how this is done? So how do we prove this? So the here's okay. So the point is that okay, maybe before proving this, let me yeah. So we use the following. So we use the following fact. So lemma, which is essentially due to the linear. So let X be a smooth variety. Then there exists a natural isomorphism of C infinity X modules between so the O of so it's a natural isomorphism in M that lives in variation of X substructure in X. So sigma M is this is this OX module underlying M tensored with O C infinity X. So let's say affine, smooth affine, just for simplicity notation. Okay, so we have this. There's an isomorphism between this and the same thing, but where we first apply the graduation for the weight filtration. Like this such an isomorphism, which is moreover compatible with, so it's natural in M, but it's also compatible with tensor product and base change. All right, so I will not really describe exactly, the proof of this, but I'll just give you some facts. So, all right. So the point is that so this guy OM. So this is this C-infinity module OM tensored with OX. Sorry, with C-infinity X over OX. So this guy has 3 filtration. So it admits 3 natural filtrations. So there is a weight filtration. W. There is the Hodge filtration. So these are part of the data of a variation of mixed Hodge structure, and then there is the complex conjugate of F, which is F bar, and yeah. So the reason why we do have such a conjugate is that somehow, at least locally on X, this has a rational basis, if you want. Sorry, this module has a rational basis because it's given also. In the data of a variation of mixed structure, we have also a local system, a Q local system, right? So this gives us at least locally on X a Q structure. So we can speak about the complex conjugate. All right. So these 3 filtration these 3 filtrations are opposite in the sense of the ring. So this is somewhere in Hodge 2. Hodge 2. The definition of an opposite of opposite 3 filtration. and then somehow the so the proof of the lemma then is to apply a general fact which is also to be found in Hodge 2, which somehow say that whenever you have an opposite 3 filtration, you can construct some you can show that these filtrations somehow split naturally. There are natural splitting of these filtration whenever they are opposite. Okay, so by Deligne, we know that these filtrations have natural splitting. So as far as I understand, the splitting is not unique. There are choices. You can define many splittings, but all these splitting are really functorial in morphism of filtered object. So if you have two two triple, I don't know how to say it. So if you have two objects having opposite 3 filtrations and the morphism between them which is compatible to the filtration, then the morphism will be compatible with the splitting. Okay? So it will be given by direct sum on the splitting, and also the splitting will be does not really depend on the splitting depends on some discrete data, and so in particular it will be also preserved under functors, exact functors. So and so on. So I just give you the formula. It's really kind of weird. I mean, I don't understand really what's going on here, but so what Deligne does, he defines sub-objects like this. So of course we assume that you are in an abelian setting, so we can speak about sub-objects. So he defined sub-objects as follows: D PQ as the following intersection. So this is the weight filtration intersecting with FP, and then he does another intersection with again omega plus Q, now intersected with the opposite to the Hodge filtration, plus an infinite sum from 1 to infinity of the weight filtration P plus Q minus I intersected with F bar Q minus I plus 1. Okay, so these are subspaces, and then he shows that under the assumption of the filtration being opposite, that the direct sum of P plus Q equal N dP comma Q. This is, of course, first it injects into Wn, and then he projects to the degree Wn. And this is an isomorphism. So here there are some choices that I'm not saying what they are, but so there are different formulas like this that will have the same conclusion. All right. So and so in particular, this gives a splitting of the weight filtration. And then one showed that the splitting is also, satisfies the properties that we want. Right. So this is a lemma that yeah. So let me tell you how to finish with this, using this lemma. So how to conclude? So, step 1 of the proof. So by this lemma, we know that, so we see that the algebra O A tensor O C infinity. So this is an algebra. The unit of this algebra has a section. So the unit of this has a retraction. Why is it, so this is due to the fact, I mean, yeah, okay, the reason is that by this lemma we know that this is the same as the weight filtration on A O tensor O C infinity. Okay, and now we can project to Guru 0, and using the assumption of the theorem, we know that this is the same as the unit. Okay, so the Guru 0 is just the unit meaning C infinity. Okay, so because the Guru 0 of A is just the unit as a variation of X construction by assumption. So we have a splitting, and now there is a second lemma which tells us that this is now fine. So again, it's in a general situation. So let E be an algebra with a unit with a unit that's split with a unit that's split. Then these complexes is 0. Let me quickly say why. So maybe here. So this is very easy. So you just write down a homotopy, and so the complexes looks like this. So this is let's say for n equal 2. So this is C less than 3, and C less than 2 is like this. And here you have 0 here. And so you want to show that the projection is homotopic to 0. So this is given by the identities, and then 0 here. And the homotopy will be given by the section to the unit. And this will be identity tensor section. So on. Okay, so this is the proof of part 1. Yes, I think so. Yeah, that's true. Exactly. let's now so let me explain how to finish the proof. So this is part 2. So we want to somehow to get rid of this C infinity, right? So we want to get rid. I mean, not only, but yeah, get rid of this C infinity. All right. So to do this, we argue as follows. So let's consider the functor y for Yoneda, of course. So going from V variation of mixed source structure, anything, to the category of DG modules over the VMH. Okay, so what do I mean by this? So VMH is this. So so this is, remember, this is a category of ind variation of mixed source structure. These are just the finite type one, finite rank. A DG module on so this is an Tannakian category, so it's abelian. So a DG model is just, I think, just a functor from this to complexes of vector spaces, an additive functor. Okay, so just okay. So and we have a Yoneda embedding, which does what you think. So essentially takes M, so it takes a module and takes it to the thing that is represented by M, namely R home this value. And not surprisingly, so of course this extends to complexes. And it's not surprising that this is equivalent equivalence. So y, or I don't know if, okay, let's say y is equivalent equivalence. Or just induces an equivalence up to passing to the homotopy categories. And in fact, more generally, one can show that it also induces an equivalence when you pass to category of pre-sheaves. So the induced functor from pre-sheaves on C, let's say complexes, VMH to pre-sheaves this is also equivalent equivalence. So induces an equivalence when you pass to the homotopy categories. And so to prove what you want, so we our map is, so that we have this b less than n, maybe plus big N, plus something, dot. So we are interested in this map, and this map somehow lives in the homotopy category of this of here. And so to prove that this is 0 in the homotopy category here, it's actually enough to first map it here and then study this map on this side. Okay, so we may apply enough to show that if you want Yoneda applied to B dot is strongly contractible. Okay. Now, now we use the hypothesis of this theorem. So let me maybe take some place. Right. So yeah. So now, so since by hypothesis the alpha x are Artin neighborhoods, we have also we have again this we can use this Bayesian, or at least a version of Bayesian's lemma that I mentioned earlier today, to say that this R home there. So if you want, yeah, the Yoneda embedding of M applied to N has a simpler form, which is given by the RAM complex with values in if the RAM of M tensor with N dual. Okay, so this is slightly finer than what I used before. Before I was using that I need to pass. I mean that when you pass to the generic point, you have such a things. Here I'm saying that it's actually true over Artin neighborhoods. Okay, so we have this, and so in particular we see that. I mean you could of course take the algebraic omega. You could take also the holomorphic one, but what I will take the C infinity one. So I don't know how to write this. Let me put C infinity. So I take the C infinity the RAM complex. Okay. And so now, so the point that now y, so the functor y has, so if I write it like this, has a filtration of length 2n plus 1. This is the n, which is the theorem. Simply because since the dimension of the base here is less than n, the RAM complex is of length 2n plus 1, okay? or 2n, depending on how you count. So we have this filtration, and so and the graded pieces. Let me write them. Gro D, probably here. Y. It looks like so it's essentially a C infinity omega T of F to RAM and that's right. Dual. And so it can be written as follows. So the Gro T Y at of M. This is the same as so let's see, if you apply it to n, this is given by O of n that you tensor, or maybe a dual, that you tensor over O with O of m that you tensor over O with C infinity, and then maybe some direct sum. Tensored with C infinity omega t. Okay, so this is okay. So it's a tensor product of two functors, and then with some constant object, constant. Now by step 1, we know that Gro D y what is it? b less than n plus 1 dot plus is 0 in the multiplicator. All right, so we have now a morphism of graded of filtered object, and how to say, so if you want, we have a sequence of morphism of filtered object. The filtration is always the same, has the same length, which is 2n. And we know that on the graded, each map is 0. Okay, and so it's kind of clear that if you compose 2n of these maps, then you get 0. Right? So at each step, the image somehow descends. Okay, and so this is how you get the statement. Okay. So I mean, I only promised a sketch anyway, so I think this is. All right, so now go to this next paragraph. So this will be about so-called the block Levin tower. So this will be part one, which will be the part one will be useless actually for us, but it's just a simpler situation where it's maybe easier to see what's going on. Yeah, let me maybe motivate a little bit what you want to do. So yeah, we would like, so we want to apply the previous theorem. So this theorem that give us this criterion for strong acyclicity. So to show that this chi underline Hodge is strongly contractible. Actually, this is probably, I mean, yeah, I'm sure that this is actually wrong. I mean, this is actually not true. This is actually false. So yeah. So we will. I'm not claiming that this guy will be strongly contractible, but we would like somehow to maybe apply the theorem maybe to some version of it for which we can hope to show that. All right, so let me maybe tell you, or let me explain to you why. I mean, it's unreasonable to expect that this is strongly incontractable. Why the previous theorem does not apply directly to this guy. So maybe let me first remind you that this is the Church complex at x0 by construction. Right, so so of course, as I said, we would like to apply to take C to be this triple integral, and the algebra will be given by this x0. Now there are two problems. I mean, there are two issues to apply. Theorem. The first one is that so the two functor VHM 0, 0 is not of the form we want. So it's not given by it's not like that we have a functor from here to schemes and then we compose with VHM. Okay. In fact, what we have is rather the following. We have a functor from this category to the category of regular finite type stratified tangential morphism, and then we compose with VHM. Connect VHM is an open stratum, and this is not really of the form that we can that we have in this theorem. And in fact, this is I mean, one might say that this is maybe not such a serious restriction, but it's actually, if you look at the proof, it's kind of difficult somehow to do the proof in this context. And the reason why is that so here we have so the morphism between so the functor that appears here, there are inverse images along these tangential morphisms. So in particular, we have these limiting functors that appears, and this limiting functor they don't have a coherent support, right? So we don't have we cannot just take variation of Hodge structure and look at the RAM component and look at O. I mean, the functor O that I use in the proof does not exist in this context. Okay, and also yeah, so somehow the proof does not work as it is. So this is one problem, and second problem, which is clearly a serious one, is the fact that there is no bound on the image, on the dimensions of the U's that appear. Right, so this functor here sends a tuple U to U, but U can be of arbitrary dimension. There's no we don't know that U is of dimension 5 or less, right? So we don't have such a bound. So these are the two problems, and in fact, the solution will somehow will be for both problems together. In fact, if we can somehow bound the dimension, then we will be able to deal with this problem also. Yeah, and maybe I will say something later about this. I mean, if you remember that there was two filtration on the categories A's. In the last lecture, I defined two filtration. One is by the dimension of U, and the next one, and the other one was by the dimension of it was this number dB of U, which was essentially somehow the image of some the dimension of the image of some map associated to U, right? So it was U mod out by the torus. So we have these two numbers, and this induces two filtration. If we can bound the dimension, then the other filtration will have only finitely many steps, because of course dBU is less than the dimension of U. And then we can. There is a construction which essentially is like passing to the graded of this filtration on these categories, and when you pass this to this graded, then you can rewrite the composition without involving tangential morphism anymore, and then you could apply the theorem to this in this situation. Okay, so I try to say maybe some more things about this later, but so these are the two problems that we need to face. And yeah, so the idea is that maybe take some place. Yeah. Do you have? Can you change it now, or just?
There is one inside there.
I don't know. Do you want to do this? Well, I'm erasing the blackboard. If you want, I mean.
Yeah, I only have one in the mid.
Oh, okay. But you could put one with the older one.
Yeah. Screen again. Screen.
All right. So let me maybe informally say what is the idea to deal with these two problems. So, roughly speaking, so we will see that. So remember that there was this functor p upper big pi upper star. Right. So which involves computing cohomology on some schemes. And what are the schemes that appear? They are rather simple, but so they are of this form: E bar some power times find some power, maybe, and then maybe times some test scheme X. Okay, so there was yeah. So the idea is that so the idea is the following. So by replacing these schemes by some big enough or maybe small enough small or big, I don't know. Some let's say well-chosen oppens, or actually pro-oppens. One can ensure that there is a bound, suitable bound, on the dimensions of the U that appear for any relevant relevant 5 tuple. Right, so what I mean by relevant 5 tuples, so if we want to compute the cohomology of this guy with value in I don't know, let's with value in these guys, in these complex. I mean, not this one, but maybe. Okay, so you want to compute the cohomology of these schemes with values in here, and to do this, we don't need all the values of these on all schemes. I mean, there are some particular schemes that we, for example, blow-ups of these guys, maybe replacing them by some étale neighborhoods and so on. These are relevant to the computation of the cohomology. And also the flags that are in these relevant schemes, they contribute to. I mean, they give us 4 tuple like this, and then there is this U here, which depends on D. And yeah, if we do things carefully, we could hope that the U's that appears have small dimension. And it turns out that in fact U tends to have a small dimension. Because it's somehow, I mean, the idea is it's some kind of you see, the U is, you have this diagram, and U is here. It's some kind of push out, and this U tends to be smaller in general. I mean, it can be very big sometimes, but in general it tends to be small, and one has to show that it's if you choose the right open, you could ensure that U is small, and without somehow killing the whole complex. Okay, so this is somehow the idea. And so the opens that we will use are actually, they will be quite simple in principle. So that they are just you fix an integer, and you look at all the open subset whose complement is of codimension bigger than this integer. Okay, so this is the idea. So you look at here, you look at all opens such that the complement has codimension, let's say, bigger than 5. Okay, so this gives you a pro open, and the idea is to replace this by this pro object, okay, without killing. Again, I mean, the important thing is that you don't want to kill the whole cohomology. Okay, so you want to still have something when you pass to the limit. All right, and so there is a machinery to do this, which is this Bloch-Levin tower. So I start by describing this Bloch-Levin tower in the case of schemes, not double star schemes, just because it's a simpler situation, and maybe and then the construction are somehow nicer and maybe easier to remember. And then, as I said, this will be kind of useless for us, and then maybe next time I will explain the actual version that I need, and yeah, maybe also try to finish the proof. Okay. So today I will just somehow, it's a kind of preparation for next time. I just explain this construction for schemes. All right. So. when did you say that you need to leave, Andrew?
1 hour more.
Oh, okay, good. Okay, so let me remind you of some notation. Okay, so we have this ordered set Pn, which is a ordered set of non-empty finite subsets of the integers. And we have a diagram of schemes indexed by this ordered set, which is given by the functor that takes a finite subset I and associates this to this spectrum of this usual thing. All right, so we endow AI with a natural stratification, which is a regular one, which is induced by which has as a boundary the divisor defined by the equation product of the TIs is 0. And for so given a subset G inside I, I denote by partial index G AI. So this is the image. So maybe it's just like a strict one. This is the image of the natural inclusion. So this is a subset, intersection of faces of this divisor. All right, so. So here's a remark. So recall that also I've been denoting pi, the obvious projection. And so we define pi index n of f. So f is a f is complex or just pre-sheaf on finite type schemes over AP, Pn. Okay, so given such a pre-sheaf, so I define pi nf. So this is complex. So maybe just let's just take a pre-sheaf. So this is a complex of pre-sheaves which is given as follows. So pi n m of f is a direct sum of I inside 0 n. The cardinality of I is n plus 1 of pi n index if, where pi n there is no need to n here. Why pi if? This is simply the pre-sheaf that to x takes or gives fi aix. Okay. Right, so this is if you want to, what you do, you take your f, you restrict this to schemes over ai, and you take the direct image along the projection. This is pi if. Okay, so there is a complex. So we have seen this construction before. So there are natural map between these guys, and they form a complex, and then one passes to the limit. So pi f is co-limit over n of pi nf. Okay, so this is a way to so out of a complex of pre-sheaves, or out of a pre-sheaf on schemes over this diagram, when one construct a single complex of pre-sheaf, which is pi f, and it is some kind of it's a version, if you want, of the singular complex of Susslin-Voyvodsky, but somehow that is a bit more general, because it takes as an input, it takes a pre-sheaf on this category instead of just a pre-sheaf on scheme over the field. Okay. So we have this. This is just to remind you about. So I mean, maybe I should say. So this is just another name. So if you want pi of f, this is the same thing as dot pi lower star. We have seen this before, so I want to give another name to this construction. Okay, so now I want to introduce a new construction, which is which has to do with some. I mean, one could call it the block complex in some sense. So Here's are some more notation. Okay, so let's fix a finite subset on empty of the integer. So we let A with a hat and I be the pro be the pro AI scheme, which is obtained by successive blow-ups of faces. So let me maybe say it in words. So we will come to this later, maybe next week. So so this is the thing that follows. So you have this natural divisor partial of AI, and so you call the faces just an intersection of divisors. So the faces are these guys here. And so blowing up faces mean you blow up such a face, and then you look at the inverse image of this divisor. This gives you, again, a normal crossing divisor in the blow up, and then you can speak about faces in the blow up, and then you blow up again some face in the blow up, and so on. Okay, this is called the successive blow up of faces. Yeah, this clear. So it's not clear, but one can show that this is really a pro object in the sense that this is a co-filtered category. So that if you have two such blow up, you can refine them by a blow up of faces.
You use facts like blow up this, blow up transverse. They commute such.
It's a bit tricky.
You blow up and blow up here, it's the same as blowing.
No, I think this is not true.
I mean, if you have with transversality, there are all kinds of results about rearranging orders of blow ups.
Yeah.
Sometimes in different orders, and
but
it's tricky. It's not straightforward.
Yeah. It's I mean, yeah. I mean, there are results like everything can be defined by blow up of codimension two faces, like intersection of two divisors. But even this, I mean, if you have two such things, it's kind of unclear to me how you compare them.
Right.
I can tell you maybe an easy answer to this. I mean, you could also think about this as so that there is the notion of toroidal embedding, and these are toroidal modification, and these guys, I mean, you can think about them in terms of fans and subdivision of fans, and then I'm just saying that this is that subdivision of fans is a co-filtered category that you can, which is. It's clear, yeah. But I mean, you see, in this language, you introduce singularities, because if you have two subdivisions and then intersect them, then I mean, there are also you have to make some choices because you have to reorder the intersection, and then you don't have any more simplices. You might have, but then you can resolve these singularities and you get simplices. So it's yeah. I mean, I think, for instance, I mean, there is, I think, in the paper of Bloch, there he proved this by hand. He showed, and it's a tricky proof that so, yeah. All right, so we look at these pro objects, and so I'll denote by this is the inverse image of the divisor of A, and similarly, if I put a G, okay, all right. So now we will have now has to be a bit more careful because now that there is no clear maps between. I mean, if you have a G inside E, you don't have any more a natural map between these guys. Right. So the functionality becomes a bit more complicated, and but we have the following lemma. Okay, so for K inside G inside I in Pn, we have a natural morphism of pro AK schemes between the case boundary or the K face of, it's not really a face, but it's yeah, the partial K of A hat to partial K of AG. And they satisfy the following compatibility, or such that. So for every inclusions, L, K, G, I, we have commutative diagrams like this. So this, of course, there are maps like this, and these are obvious maps. This is inside here. Now we have these projections. This commutes. And furthermore, this triangle commutes. Right. So this is a notation to say that you can have something or you can have anything. I mean, you can have nothing. Okay. There are two cases: either partial without anything. This is the whole boundary, or the faces. All right, so let's check. I mean, let me explain the construction of these maps. So, So what we do is fine. So let's fix such an inclusion. And so we have a natural map R that goes. So it's a rational map. It goes from AI to AJ, which is given essentially by so taking a family. So this is yeah. If you want, I mean, a point here is a family of points of in A1 such that their sum is equal to 1. Okay, so and this is this goes to the following family. What you expect. So okay, so so this morphism is defined, of course. This is defined on the complement of the divisor Hj inside I, defined by the equation sum xi equals to 0. Of course, the natural map, the natural inclusion to AI, actually, of course, factors through the complement of this divisor. Okay, so now, yeah, so and moreover, so if you look at, so again, let's look at this map. R. So here we see that the inverse, so the inverse image of the divisor of AG is contained in the divisor of AI. Right? Because I mean, so saying that xj is 0, then the inverse image is just xj. Good. And so, as a consequence, we get a map, an induced map from so of the blow up of faces. Again, it's a rational map, but I just have to remove the inverse image of the divisor Hg. It goes to Hg. So So let me write the following. So we have the following commutative diagram. So write it again. So this is AI minus this inverse image of the divisor. We have this map R hat that goes to AG. So inside here we have partial G and inside this we have partial K. Okay, so we have this sequence of maps. Now there are this obvious projection to AG. This is R. So here we have E minus HG. H here, so and we have partial K, AG, I think AG. Okay, and so of course this is identity. And therefore, this is so the composition here is just the inclusion of the K faces in AG, and so this show that. So as a consequence, we see that the composition of I mean, of course, I think this is not needed. So the composition of the first line factors through partial K G. Okay, and this gives the map that we want. So I mean, I will not, of course, not check the compatibilities of this map, but let me just say one word. So the triangle in the statement, which may be a bit maybe surprising, it somehow simply comes from the fact that if you look at these rational maps, so one does have a commutative triangle like this. Also. All right, so we have these things, and okay, so we use this for the following construction. All right, so let's I denote by Qn. This is the category whose object are given by inclusions. Of non-empty finite subset of a map between two such inclusions is the same thing as, so this is a chain of inclusions as follow: k prime inside k, inside g, inside g prime. Okay, so so this is of course defined in such a way that by the previous lemma, we have we see that sending such an object to the face of the blow up is a functor, is a covariant functor. Okay, so we get, in this way, we get a diagram of pro schemes. I'll also denote by Qi the full subcategory consisting of objects like this, such that G is inside I. Okay. Now, given a complex of presheaf F on schemes of finite type over this diagram. So we set pi hat index I of F. So this is this will be also a complex of presheaves on finite type schemes now over a field, and it takes X to the following thing, to the homotopy limit of K inside G in Qi of F partial K H times K times X. And here for I mean, this is a finite category, and for the homotopy limit, we just we take we take the usual simplicial or cosimplicial model. Okay, so the boost field can the cosimplicial model for this to make this somehow functional. Yeah. Okay, so by construction, there is a natural map like this. Okay, for any complex of presheaf, and pi I is the thing that I defined previously. Did I define this? Yeah, I think I did. Yeah. I mean, it's just f of AI times k. It's just
There's
time.
only a little bit confusing. F is pre-sheaf or complex of pre-sheaf.
Yeah, I mean, complex of pre-sheaf, yeah. Yeah. Okay, so I have the following fact here that so let F again be a complex of pre-sheaves on finite type schemes. And so assume that actually I don't need to, yeah. Let's just take it on I. It's enough to, of course. So assume that F is H fibrant. Okay, then the natural map is a quasi-isomorphism. Okay, so I will not prove this. It's it's a bit, I think, combinatorically involved, but